Hello students, how are you? Last time we met, I posted a video related to some concepts of complex numbers. We studied multiplication, geometrical representation, principal argument, etc. After about 6 months, we are meeting, and now my goal is to teach you about some concepts of modern algebra or abstract algebra. So we'll study many new things such as groups, rings, etc. We'll start with groups because this is the basic unit of modern algebra. So let us begin. Okay students, as you can see, the definition of group is in front of you. An algebraic structure GO where G is a non-empty set and O a binary operation defined on G is called a group. If the binary operation satisfies the following postulates, which are known as the group axioms. So what are they? Closure property. Suppose any two elements are in G, then when you perform the binary operation on A and G, then the result will also be in G. Take the set of natural numbers. Take any two elements, for example 2 and 10. Now we take the binary operation of multiplication, then 2 plus 10, which is 12, is in the set of natural numbers. So it satisfies the closure property, but we'll see later that it is not a group. So instead, take the set Z, the set of integers. Now minus 2 and 5, the sum is 3, which is in the set of integers, that is Z. Associativity. It satisfies the associative property. Again take the group Z plus, so 3 plus 10 plus minus 3. You can do this addition in any way, but you will get the same result. Now, a natural question arises that we have talked about associativity A, O, B, O, C, okay, is equal to, but why not this? This property, as you are very well familiar, is called the commutative property. But we will see that in mathematics this is a stronger property compared to associativity, and it is not satisfied by all the groups. Okay, so for group axioms only four properties are needed. Existence of identity. There is an element E which is the identity element. If you perform the operation EOA, then you get the element itself. EOA is equal to A is equal to AOB for every element in G. Okay, so such an element is called the identity element. Now, as the name suggests itself, this holds the element holds its identity. So it will not lose its properties or its character or its identity. That is why, or we can say the element is invariant under that particular operation. The last one is existence of inverse. For every element A, there is an element, or we can say there is a unique element A inverse, such that A inverse OA is equal to E is equal to A OA inverse. Okay, and as we know, E is the identity element. So for each A, such an A inverse exists. This A inverse is called the inverse element. Now take the group Z plus, where Z is the set of integers, plus is the obviously addition operation. So in this case, Minus 3 is the inverse of 3, minus 4 is the inverse of 4, and likewise. If you add minus 3 and 3, you get 0, which is the identity element of addition. Okay. Similarly, you take the group Z dot, where dot is the operation of multiplication, and you have to take the set Q of non-zero rational numbers, because for 0 we don't have the inverse element. 1 upon 0 is not defined. So you take the element 2, its multiplicative inverse is 1 by 2. 2 into 1 by 2, or 2 dot 1 by 2 is 1, which is the identity element of multiplication. Next definition is of abelian group or commutative group. If it satisfies the commutativity property or commutative property, A of B is equal to B O A. Now, why this property is told in a separate way? Why not is it added along with the group axioms? Well, I'll give you one simple example. Take the set of all matrices, n by n matrices. For example, if let us take 2 by 2 matrices, then AB is generally not equal to BA. That is, the matrix multiplication is not commutative. Only under special circumstances a group is commutative. That is why such groups are special. They have a special name, abelian groups. We have some examples of group, as you can see, Z plus, okay, which is the same as I, Q plus R plus. They are infinite abelian groups, with plus being the binary operation. The set of all even integers including 0, E with addition as binary operation forms an infinite abelian group. As I told you, we'll only look at the theorems, we'll not go into the proofs. So theorem 1 is uniqueness of identity element. The identity element in a group is unique. How will you prove this? Just let us look at the basic outline of the proof. We will prove by contradiction. We will take, suppose there are two identity elements in the group. Then by applying some operations, we'll see that both of them are equal. The inverse is also unique. For any element A, the inverse element A inverse is unique. This is also an interesting property. If the inverse of an element A in a group is A inverse, then A inverse whole inverse is A. That is, the inverse of the inverse is the element itself. Fourth is an important property too. Reversal law of inverses. AB whole inverse is equal to B inverse A inverse. This property is also known as Schuh-Stokes property. Now, generalized reversal law. We can generalize this to more than two elements. For any number of elements, the whole inverse is, you just reverse them. That is, in a way you flip them and take the inverses, you'll get the same result. Cancellation law. This is a very basic law in fact, but you must read them. AB is equal to AC, this implies B is equal to C, and B is equal to BA is equal to CA, this implies B is equal to C. We can cancel from the left in the first one and in the second one from the right. So this is known as appropriately left cancellation law and right cancellation law. Now, order of an element of a group. Basically, the definition is that we take an element A and we compose the element A with itself. Now, the number of times we have to compose the element A with itself such that we get the identity element E, that number, let's call it n, is called the order of the element in a group. Let us take the element A in any group, say G, and the operation is O. Then A to the n is equal to E, or we can say A O A O A O A dot 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 O A. This is done n times in such a way that we get the identity element E of that group. Then this number n, okay, this one is called the order of the element of that group. Now there is an interesting definition. If the order of every element of a group G is finite, then group G is called torsion group or a periodic group. Now they have given some examples here. This is a 4 element group, okay, 1 minus 1 I minus I, and the operation is dot obviously. And another group is 1 omega omega squared, operation is dot. Can anyone tell me in the comments which type of group is this? Actually, this group I will tell you here is the group of cube roots of unity. Okay, the omega is, it has a certain expression with radicals. That is why to make it, to simplify it, they have given it a symbol. Torsion free group is the opposite of torsion group. A group G is called a torsion free group if the order of any element except the identity element is not finite. Okay. So they have given some examples: Z plus Q plus R plus. Theorem: the order of every element of finite group is finite and less than or equal to the order of the group. Now from here, group theory becomes a little bit complicated. We take groups modulo something. Okay. We can take any operation, addition or multiplication. Now basically what we will do is that we want to construct some kind of finite group, that is with a finite number of elements, and we will do this by using some kind of trick on infinite elements. So let us understand what we mean by addition modulo n. Suppose we have any two integers a and b, and we perform the sum a plus b. Okay, then let us understand here. Operation of addition modulo n is defined as the least non-negative remainder when the ordinary sum of a and b divided by n. Take any number n, for example, let us take 7. Take any two integers 1 and 2. So 1, or let us take greater than 7, 8 and 9. 8 plus 9 is 17. Now if you divide 17 by 7, which was our n, then we get 3. The remainder is 3. Okay, because 7 2s are 14 plus 3 17. Now this 3 is our is the element of our group. Okay, now we will take this 3 in our group, and later on we will see that there are only certain elements in our group, that is the remainders are, we can say, periodic. The remainders will repeat themselves. That is why such groups are special, and they are particularly used in number theory. Now let us see what example they have taken in the book. 16 plus 5, 7 is equal to 3. The sum 16 plus 7 when divided by 5, so 16 plus 7 is 23 divided by 5, so 5 fours are 20 plus 3. You get the remainder 3. So you get the remainder 3, which is the least non-negative remainder. Similarly, take another sum, 5 plus 8, 3. You take the sum 5 plus 3 and divide it by 8. So you get 5 plus 3 is 8 divided by 8, you get the remainder 0. Okay. Now if you have studied thoroughly the Euclidean division lemma and such things, let's not use complicated names. If you just know your usual division from class 4 and 5, you will know that if the remainder exceeds the number, that is the dividend, you can divide it again. Okay. So we can say that the number of remainders will be from 0 to n minus 1 only, because in case of addition modulo n, because as soon as the remainder becomes n, you can divide it again and you will get 0. So how many elements will be in that group? The number of elements will be n. Okay, 0 to n minus 1. The notation is important here. If a and b are two integers such that a minus b is divisible by n, we can write a congruent b mod n. Okay, we have some theorems here. A congruent b mod n, take the theorem to a congruent b mod n and c congruent d mod n, then a plus c congruent b plus d mod n and ac congruent bd mod n. Okay. Another kind of operation is multiplication modulo n. It's nothing but if a and b are any two integers, then the operation of multiplication modulo n is defined as the least non-negative remainder when the ordinary product of a and b is divided by n. So again we are seeking the remainders here, but the operation is different here. 7.54 is equal to 3. The product 7 into 4 is 20 divided by 5. Sorry, 28. When divided by 5, 5 5s are 25, so you get the remainder 3. And this is our remainder. Later on we will see that these remainders under the particular operation of addition modulo n or multiplication modulo n form a group. Okay. There is a rather useful function which is used various times in several branches of math, which is known as the Euler's phi function. So Euler's phi function is defined for all positive integers n by phi n is equal to the number of positive integers less than n and relatively prime to n, and also phi 1 is equal to 1 for n is less than 1. Now what do you mean by relatively prime? You know what is prime? 2, 3, 5, 7, 11, 13, 17, 23, 29, etc. These are the prime numbers. From 1 to 100 there are 25 prime numbers. That is 25% of the numbers are prime from 1 to 100. But as you go on and on, the percentage of prime numbers will decrease. However, there is a famous theorem and its proof is due to Euclid that the number of prime numbers or the number of primes is infinite. The proof is very simple and we need not go there, but just you should know that there are infinite number of prime numbers and one is neither prime nor composite Okay. But what is relatively prime? Relatively prime numbers are also known as co-prime numbers. Suppose take numbers 4 and 8. 4 and 8, they have a common factor of 2 and 4 also. 2 will divide both of them, 4 will also divide them, 1 will also divide them. But what about 2 and 11? Or take some non-prime numbers, take 4 and 9. Any number apart from 1 can divide them? No. Only 1 can divide these two. So these numbers are prime relative to each other, or with respect to each other. We will say these numbers are relatively prime, relative prime or co-prime. So Euler's phi function, this is for such numbers. Phi n is the number of positive integers less than n and relatively prime to n. Okay. Now suppose we have a prime p. Phi p is equal to p minus 1. Similarly, another result is phi p power n is equal to p power n into 1 minus 1 upon p. For every n, p is in the set of natural numbers. Phi mn is equal to phi m phi n if GCD mn is equal to 1. GCD is the greatest common divisor of m and n is 1, or you can say that m and n are relatively prime. Now what is a subgroup? As the name suggests, subgroup, that is a part of a group, but the definition is more complicated. Subgroup is a part of a group, but it is also a group in its own regard. So let G star be a group and H subset of G be arbitrary such that H is not empty. So for every A and B in H, this implies, okay, this is not the definition, sorry. Subgroup is Subgroup is any non-empty subset H of a group G, which is a group in itself. That is, H is also a group under the same operation. Suppose we take the set, take the set of real numbers and the operation of addition. Now, as we know that the subset, the set Q, the set of rational numbers, is a subset of R. Now, Q is a subset of R. Q is obviously non-empty, and Q plus forms a group also. So we can say that Q plus is a subgroup. Okay, now algebra of subgroups. If H1 and H2 are two subgroups of a group G, then H1 intersection H2 is also a subgroup of G. That is, the intersection of two subgroups is also a subgroup of G. Okay, and we can extend this theorem to arbitrary intersection. That is, any number of subgroups when intersected, you'll get another subgroup. Okay, this theorem, you must know this also. Union of two subgroups is not necessarily a subgroup. For intersection, you have this theorem, and even for arbitrary intersection too. But for union, it is not applicable. Okay. Okay, students, that's all for today. And from next time, I will try to make more instructive and informative video. Today, I was not very well prepared. So as you can see, the screen is also not stable in one place. But next time we will look at some concepts in greater detail, and I want you all to stick up with me so that you can get great insights into mathematics. And if you have any questions, you can drop in the comments. If you like my video, please give a thumbs up and subscribe to my channel and share it as widely as possible. So thank you. This is Shlokan Srivastav signing off.